Welcome back, everybody. Let's just jump into this. Last time we were talking about an example, and I want to generalize these different procedures. So some of what I'm about to say is almost correct, and I think that when we see a couple examples, you'll be able to generalize. But we have three different procedures for coming up with estimates that we've looked at. And there's more procedures than just these, but these are kind of your typical. And there's no guarantee that these methods are necessarily going to give you really good estimators. So later on in chapter 7, we're going to discuss properties of good estimators. So before we jump into this and start generalizing, just ask this question. What's a good property? For an estimator to have? Anything?
Unbiased.
Unbiased. This is the one everybody always jumps at first, right? Unbiased. Oh, not dark. Unbiased. Let me just ask why.
Because then your estimate's not going to be off.
It's not going to be
You have
off.
confidence in your estimates?
Yeah,
Does
so
that
maybe.
be the right thing?
Maybe. So Stephen thinks it's the right thing to do. You don't want to be off. Let me just say something. If we're estimating something continuous, I guarantee you're going to be off. Right? Probably not going to nail that thing. So if I pick some key, arbitrary key that could live anywhere between 0 and 1, and then generate some data, chances are you don't get the exact key. Guaranteed to be off.
Or maybe it's the confidence that as you like crank up n, that you're going to get closer and closer.
Okay, so you just invoke the word, right? So confidence, what is that? We like these words. Feel good about it. Anybody else help out Stephen? Maybe why do we like unbiased? Okay, how about this? How about another criteria?
Like small variance?
Small variance or something like that. So, variance is small. So usually we'll take those two together, you know? And so just one of these isn't good enough. So what's wrong with just being unbiased? Augur.
Well, from sample to sample, you could have so much variability.
Maybe, but just, yeah, exactly. We have to account for the variability. Can't forget about it. Unbiasedness has something to do with, on average, good performance. So we also need to think about how stochastic is our estimation. How wayward is it? So just give me another criteria.
So I'm just thinking like unbiased is for the first moment and the variance is for the second moment. So the two together is a good estimator.
Yeah, maybe. So 2 is better than 1. So that seems pretty good. What about another property? What would you want?
Small MSE.
Maybe small MSE, and if you put these two together, you get there. So it turns out MSE is the bias squared plus the variance. So we'll see that in a couple days.
Consistency.
Consistency, I like this one. So what does this mean, consistent? Let me just draw you a picture while we're thinking about this. Maybe my truth is theta, and maybe I have some procedure. Maybe this is really far out here. So maybe sometimes I pick the answer to be here, theta. So my theta hat is over here. And then sometimes my estimator maybe theta hat is over here. And then sometimes it's over here. And then sometimes it's over here. On average, I might be really close to theta, but I'm never actually there. So it's jumping all over. So you might imagine I've got two different estimators. I'll say this is theta minus epsilon, but epsilon is big. So I'll just call this something big. And this is maybe theta plus something big. And maybe I call this, here's maybe theta hat is one possible answer, or maybe my theta hat is sometimes over here. I'm just drawing a picture. And so if whatever is big is the same, then my symmetry on average, I'm right at theta. So I'd never give you anything in the middle. That would be bad. So, but on average, it's giving you the right thing. So that's why we don't like unbiasedness just on its own. I think we like unbiasedness because it makes us feel good. And that's all there is to it. So, but consistency, this is a little bit more. This is at least a sanity check. So consistency says that theta hat, whatever my procedure is, will go to theta as n gets big. So of course I want that. If you gave me all the data in the world, I shouldn't have to be uncertain anymore. Show me everything. And so I like this as a sanity check. And we can kind of think about our different estimators that we came up for P in our Bernoulli example. So we came up with answers that looked like X bar. And we came up with, in the Bayesian context, something that looked a lot like X bar. So our Bayesian answer, I'll say Bayes, let's write down Xi as from Bernoulli. P. Everything's I have to do here. Most seem to freak out if we don't do that bad thing. So we came up with, at least in some case, we came up with a MOM estimator was X bar. Sum of the xi over n. We came up with our MLE. This was X bar. And then this thing looked like this. Xi's plus 1/2 n plus 1. So this was assuming our prior distribution was a beta with my two parameters, half and a half. So when I had a half and a half add up in the denominator, they added 1. So all of these estimators, they're kind of pretty close to each other, obviously depending on how big is n. But as n goes to infinity, in that example, this thing converges to p. As n goes to infinity. That's true over here as well, and that's true because it's the exact same thing. So this estimator has a little bit of bias to it. And we've kind of liked it. But maybe that's good. Maybe the trade-off in terms of its variance, maybe that's a good trade-off. We'll have to decide a little bit later. So X bar is not the only estimator in town, but asymptotically, this looks a lot like X bar. That was relatively large, and no big deal. And so they're all converging to true P. So we want to think about all these things kind of together. So I'll ask some questions as we derive some estimators. Are things consistent? That's at least a sanity check that if I had everything in the world, I should be able to tell you what the truth is. So if I knew everything. Unfortunately, we never do. I'll just give it away if it's not clear. Quite often I'm willing to give this up, but I don't give that one up. Now, I could think about estimators that have really small variances. So we don't want our variances to be too small, right? There's kind of this weird trade-off. Let's just imagine I'm trying to estimate what theta is in this fictitious example, and I say theta is 7. My estimator's theta hat is always 7, no matter what. So I do my simulation study, no matter what data I see I give you, 7 back is the answer. So, very low variance. That's terrific, right? Just brought down the variance. If the answer is not 7, I'm horribly biased all the time. We need to think about all these things together. We have to get a little bit more formal and decide in which way are we measuring our errors, and that'll determine which estimators we might want. But hopefully one of these days we can get away from just thinking like, oh, it's unbiased. We'll see an example in a couple minutes. Okay, let's just generalize. So method of moments. And let's just give this problem a little bit of context so that we know what everything is, but theta usually means the same thing. So I'm going to say xi's are coming from some model. fx given, I'll make this cap theta. So that's my cap theta, that circle in H. People don't know what that is. That's my capital theta. And I'll just tell you what that is. This is going to be theta 1, theta 2, out to theta p. So I'm going to imagine that I've got p parameters that I'm trying to estimate. This is your p parameters. So method of moments is something like this. So what I'm going to do is I'm going to write down some empirical moments. And then I'm going to write down some theoretical moments. The idea in method of moments is to compute things like this. Sum of the xi's divided by n. I goes from 1 to n. That's my first moment. My theoretical moment is just this thing right here. So if you told me what the model was, I could compute this for you. So this is going to be x times f of x given theta. Dx. And I'm going to integrate over the whole space of x. So it's a calculation you can do. If I tell you the model, at least in principle, you can write down what this moment is. I'm going to do it again on the second moment. I goes from 1 to n. Then I write down my second moment. So same sort of thing. X squared fx given theta, integrate over x, whole region of x. And I'm going to do this p times. So my peak moment looks like this, xi to the peak power divided by n. I goes from 1 to n. and I can compute my peak moment. So method of moments is a technique where you equate these things, and then you solve for theta. So typically, this is probably the way you would do it first. And then you would decide whether or not this was a good approach. We're still going to need to evaluate whatever estimators we come up with. So all of these techniques are just procedures for coming up with an estimator. There's no guarantee that this is going to give you a good estimator. It's just some method. So method of moments computes equates these to each other. So what we're going to do is we're going to set, I'll say expectation, and I want to point out that these things are functions of whatever these parameters are. So I'm going to have p equations, and I've got p unknowns. And so presumably there's some solution to that. So I'm going to set x, say raised to the j power, is going to be equal to, and let's give these some names. I'll call this M1, this MT, this one's M2, dot, dot, dot. So we'll set these, the MJs, and we'll do that for all of our J's. J's goes from 1 to P. And solve for the thetas and set to theta hat prime. So you're going to solve those for the thetas, but as soon as you solve them for the thetas, you're going to write a hat over your thetas. Because they're not the truth. There's something close. So that's method of moments. In general, I'll just make a note. Note, we can also do this. So there's no unique way of doing this. I could end up writing down expectation of fj x. So this could be some function. Over here, I'd let this be the polynomial powers. So it could be any arbitrary function right here. And I could set this equal to integral f x j. Probably should have used a different function. Change the name of that. Let me call this G. So this will be G right here. I've already used F. Try not to overload the notation too badly. Dx. Integrate over the whole space of x right here. And you're going to do this for j goes from 1 to p. You might have expectations of p different functions, and you're going to set them equal to these things. This right here is going to be a function of cap theta over on the right-hand side. So I'm going to have to introduce p equations to solve for my p unknowns. So the thing that we learned back in high school that we could do.
What's the empirical moment in this case?
Yeah, that's cool. So this is going to be sum of the GJs.
Okay.
That's just what we think it is. So you're going to set them equal to those. So you just match the empirical thing to the theoretical thing. Method of moments does not give you a procedure for picking these different G's. A lot of people start with their first moments right here. I'll make a point right now. Whatever I pick G to be, it should contain the sufficient statistics. So I should have functions of the sufficient statistics when you do this, but that's not a requirement of method of moments. I can just tell you that if whatever you're doing doesn't involve your sufficient statistics, you're getting ready to be flogged by somebody else. They're going to teach you. So if you didn't build this out of the sufficient statistics, there's something called route lateralization that you can do to fix up these estimators. We'll get there in a couple sections. We'll go through all that stuff. Let me just ask the question. Method of moments, is it consistent? Just do our sanity check. Question. Are MOMs consistent? Yeah. So Peter says yeah. How come?
I think when you run the version of the example, he said the same version. Yeah, version C.
Yeah. So there's just one fringe case that we have to cover. I can't pick my G's in such a way that I don't see the P unknowns appear. So you could imagine if I picked G's to be some silly function, that my expectations are all something like zeros, and they don't contain my key parameters. So they're consistent so long as you introduced in your theoretical moments the key parameters. So you could imagine cases where the parameter doesn't show up. We'll look at an example in a minute. So yeah, the answer is yes, because expectations are consistent. So our averages are consistent. Why are our averages consistent? Why do these things converge to that?
By law of large number.
Law of large numbers is good. Anybody else have another?
Oh yeah, I was gonna say like Berkinson.
Yeah, CLT. And so CLT is a little bit better than just law of large numbers. It's telling me how I'm getting there, but law of large numbers does it for us. And so it's converging in. So our averages follow laws of large numbers and they converge. So I'll say in general, yes. So long, and I'll just make my note, as my moments, my theoretical moments, contain all of these parameters. Theta 1 up to theta. I'll show you an example where it doesn't work out. So let's just get another procedure down on the board before we compare. So yeah, they're consistent. That's kind of nice. It doesn't mean that necessarily that estimator is good. And in fact, in this procedure, you could even be outside of the bounds of the parameter space. There's nothing enforcing that. They have a good example in the book where you're estimating n in a binomial, and they give you a negative n is what the method shows. So look at that example. But I'll show you another one in just a second. So in general, if you just not pick your g functions arbitrarily in a silly way, then it is consistent. Which functions do you use to match the moments? I don't have a lot of guidance on that. Make sure they have something to do with the sufficient statistics. In general, I don't use this approach. Let's look at a different approach. I think everybody is, at least once upon a time, seeing good uses for MLEs. So the MLE stuff is just your calculus 101. So you maximize the function. Maybe you can do calc. So MLEs. Maximum likelihood estimators. So what are these things? Basically what you do is you take your derivatives with respect to your parameters. So I'm just going to write down log likelihood. It could be likelihood, the log doesn't change anything. So it's just very typical to write down log. So that's L theta, and I'm going to set this equal to 0. But as soon as I do this, I'm going to need to say my thetas are equal to theta hats. So I'm just going to plug in my theta hat for that. And I'm going to do this p times. First derivatives. So log likelihood. I kind of like this because there's no choices I need to make. So I don't have to think about which functions that I'm building expectations around and then matching the moments. This is just a well-defined procedure. So I'm just going to plug in theta hat once I do this, as soon as I set everything equal to 0. That's maximum likelihood. So we do need to check that we're not at a saddle point or that we're at a minimum. So all that same stuff from calculus. They say in the book says the form. They only do this in 2 dimensions, so I'm going to just generalize this a little bit more. So book says to form the Hessian. Itself a little bit around. So this is going to be d theta 1 second derivative log likelihood given x. This is just the second derivative matrix. These are going to be your mixed partials. So d theta 1, d theta t log likelihood. So you're going to fill this whole thing out. So these are just your second derivatives. So this is called the Hessian. It's just your second derivative matrix. And I'll just point out that this right here is your determinant. So this is a number at the end of the day. So they just say check the Hessian matrix. But they end up saying in a 2-dimensional example, they want you to make sure that one of the eigenvalues is negative, and they want you to make sure that the determinant of the Hessian matrix is positive. What did they just tell you? Yeah, so it's true. It will be a minimum in that case. So you just write it down so we're all on the same page. They don't give you the full generalization of this. I'm not sure why. The book says in 2D, 2 dimensions, I've got a p-dimensional example, so I want to just build this up a little bit farther than says. So the book says in 2 dimensions, you want to check that H has one negative eigenvalue and the determinant is positive. What are they saying about the second eigenvalue? It's also negative. So they don't tell you that. So, i.e., second eigenvalue is also negative. In general, you want all of your eigenvalues to be negative. So what that means to me is that that space is convex. I use the word convex even if I flip it upside down. So, but basically, it looks like something that looks like this, and it doesn't inflect back up. So 0 eigenvalues tell you that there's ridges in your space. Those are flat spots. The 0 eigenvalues. And so if you have a mixture of positive and negative eigenvalues, that's telling you that the space is inflecting. And it's curving in different directions. So I'm not going to go into the full geometry of eigenspaces, but eigenspaces with either positive or negative eigenvalues, no zeros, are convex or concave, depending on how you want to think about it. So if it's all negative stuff, it looks like this. If it's all positive stuff, it looks like that. Okay.
Shouldn't the hessian be evaluated at the MLE?
Yeah, that's right. So yeah, exactly. Theta is equal to theta hat. So you're going to plug that in. So what you really want to just check is make sure that all the eigenvalues have the same sign. And then there's at least a global minimizer and maximizer, and your local minimizer or maximizer is your global one. That's why we like convex spaces, because there's only one max. So make a note, all i's need to be negative. So this is our more general form. And if you thought about the geometry of this stuff before in this way, then this makes sense to you. Otherwise, this is a new compelling fact that I'll let you study up on. This isn't a linear algebra class per se. This isn't the only criterion you need. Those maximum or minima could be hiding and lurking on the boundaries. You also need to check the boundaries of your spaces. So, and check your boundaries. If you don't like this criterion, just use the second derivative test in the way that you know it. So they're equivalent to each other. So basically you do what they taught you to do a long time ago. You maximize your function. It could be a hard problem. If the problem is multimodal all over the place, you're going to need some sort of an algorithm to find your max for you. So very typical sort of procedures, iterated, reweighted, least squares sort of procedures to find maximum. We're not going to go into all of that, but if you take an optimization class, you can learn all about the study of optimization, finding maxima or minimum. It depends on what kind of space you're looking at, how difficult that is. But at least conceptually, we know how to do this. Any questions about that? Please.
Those boundary means the boundary of parameter.
That's right, the boundaries of your spaces. So we'll look at an example in a second just to define it. But yeah, the boundary of where data lives. So in our example with Bernoulli, we need to check over at 0 and 1 as well. Make sure that our maximum doesn't live there. You can kind of remember our likelihood functions when I ran simulations. For my first data point, the likelihood function is a straight line, and the maximum is on the boundary. But then after I got a couple data points, then that thing started to look like the maximum wasn't on the boundary. You can play around with that. But your first draw, the likelihood function either looks like a key or 1 minus p, it's just a straight line, and the maximum is on the boundary. You need to check that as well. I'm never going to give you on a test a really hard maximization problem, because it's not the point that I'm trying to emphasize in this class. You got hard problems that you can solve. I want you to think about statistics. But this can be a difficult problem. Conceptually, pretty easy though. Okay, let's look at a couple examples. Really do need decision theory to invoke A's estimator, so I'm going to hold off on that for just a little while. I'll say something about it before we march on with this lecture. So here's an example. Question. Xi's coming from our normal model, mu sigma squared. I get n data points. We'll say that's I. So, our mom estimators. Here's a mom estimator. So I'm going to take my first moment, and I'm going to compute it. So I'm going to do some integration real quick. Integral 1 over 2 pi square root sigma e to the minus 1/2 x minus mu squared over sigma squared dx. And I'll throw an x in there. That's my expectation of x. Minus infinity to infinity. And I can do this integral in my head. Who else can do it? What's the answer?
Mu.
It's me. So, I just know the answer. I didn't do the integral. So, I'm going to set this equal to sum of the xi's over n. I goes from 1 to n. This is x bar. I'll remind you it's a function of n. And I'm going to set this equal to mu. But as soon as I do that, I have to put a hat on there. So x bar, moment matching. Maybe we do something like this. X squared, right here. We know what this thing is. We know that the variance of x is equal to this thing, all squared. So I can do a quick moment match and say my variance, this is sigma squared in our notation. And so I'm going to take sigma squared, I'm going to throw a hat on it, and I'm going to say this thing is, I've already got an expression for that, so this is going to look like my mu hat squared. That's just x bar. And then I'm going to subtract it from my second moment. This is a mom estimator. Just looks like this. Sum of the xi's over n squared minus sum of the xi's over n all squared. And I could write this down a little bit differently. So I could write this down as sum of the xi's minus x bar squared and this is divided by n. I'll let you work through the algebra, but that's what that expression is. So you can expand one, or wouldn't be hard to show these are the same. So this is a MOM. MLE. I'm not going to do the calculus right now. They do this in your book as an example. But there aren't a whole lot of choices here. Does anybody know what the answers are?
Should be X bar,
X bar.
and
Turns out the same.
it should also, I think the sigma squared hat MLE is the same as the MOM.
Can you say it again?
The sigma squared hat MLE, I think it's the same as the MOM one, right?
Yeah, it's the same as this thing. So they match in this case. Saying that, I have more flexibility over here on the MOM side of things than I do on the MLE side. MLE, that space is convex. If you check the endpoints, i.e. 0 for sigma, you'll find that maximum isn't there. So, and there's no boundary view. So it's unbounded. What gives? So I learned in Stat 101 to use this estimator. In Stat 101, and I just mean this kind of generally, your intro stat classes, we usually take S squared. We let that be equal to our estimator. And this thing is sum of the xi's minus x bar squared divided by n minus 1. So both the MLE and the MOM procedure gave me something different. So what kind of estimator is this? How would you tell somebody you came up with that? How could you derive it? Is it a MOM?
It could be depending on your G, right?
Was that?
It put in a G1 depending on your G.
It could. Yeah, it could be a MOM. So, and in fact, it is a MOM. Let's do that in a second. Is it an MLE?
No.
No, because the MLE solves for something different. You'll have to work through the calculus to show that. But it's just a maximization exercise. It could be a MOM. So it's a MOM. So there's not just one MOM out there, there's a whole bunch of them. Infinite collection. So where I've taken expectation of S squared, and this is equal to sigma squared, right here. So then I'm applying a function of the data, and I'm matching that. So I've applied this function to everything. And so sigma hat squared MOM, this is a different one, so I'll just write down MOM2, is going to be equal to sum of the xi's minus x bar squared over n minus 1. So what I could have done to get my MOM is I could have matched this right here, done the same thing. So I matched my first moment, and then I matched the function of the second moment. And so it is a MOM. There's no unique MOM. Phase estimators depends on your prior, what you wind up with. Let's look at a slightly different example, just so we can get the gist of it. Maybe we'll come back and we'll talk about phase a little bit. So another example. Here's xi's are coming between minus theta and theta. So the likelihood function for theta is just going to be equal to the product. I goes from 1 to n. What does this distribution look like? The density function looks like that. Is that my likelihood?
You need the indicator.
I need the indicators. So if you write down the likelihood and it doesn't have any data in there, that's a good giveaway that you didn't write it down correctly. So I need my indicator. So I'll just say xi's per bounded minus theta with theta. So I'll just write this down. This is going to be proportional to 1 over theta n. And then I'll simplify this a little bit. Delta, my minimum order statistic is going to be bigger than theta. And my maximal order statistic is going to be less than theta. So what does this thing look like right here? We can see that as theta gets bigger and bigger, this function is getting smaller and smaller. It looks like that. And this is going to be bounded by some function of either xn or x1. Anybody know what this value is? This is going to be the maximum of x1, absolute value, xn, absolute value. So whichever one is bigger in magnitude. That's your best guess at what theta is. That's what the likelihood function looks like. You know it's decaying because of this part, so don't throw that away. So you need that to define the MLE. So I'll let you think about that function a little bit, but that's what that is. Let's do MOMs. So let's try to match the first moment. This seems like a grueling calculation. So integrate between minus theta and theta, x over 2 theta dx. What's that? I'll let you do the whole thing. Now plug this in, the theta.
Is it theta over 2?
This is 0.
So
Minus the theta. So this thing right here is 1 over 2 theta. Right in the middle is 0. So that's not going to help. So that's what I was saying. Sometimes you work out your first p moments and they're not functions of theta. So you need to come up with something different. So that's not going to help me. I'm not going to match that to the empirical moment and solve for anything. So I could do something slightly different though. So I could end up maybe looking at s squared. Expectation of s squared. This might be a function of thetas. So does anybody know what this is? In this example, it turns out it's theta over 3. And you can work through that. It's a calculus problem. So that's theta over 3. So what I could, oh, this is theta squared over 3. So what you could do is take theta hat and say that's 3 times s squared. and that's a mom. Let me just ask a question. Which estimator do you think is better? I didn't work through the calculus, I'll let you do that. Good exercises, you guys need practice. Which estimator do you think is better? This one? So this is my theta hat MLE, or this one?
I'm thinking the MLE because it's like smaller dimension.
Maybe. They're the same dimension, it's a one-dimensional thing.
Oh.
It's sufficient statistics.
Yes. So one of them has the sufficient statistic in there, and one of them does not. And that's our first hint that this is probably the better estimator. Let me just ask the question, assuming that we did the calculus right, and we have this answer, is this answer consistent? It is. Is this answer consistent? Turns out yes. So under basic regularity conditions, MLEs are consistent. That's something attributed to von Mises. You might look at it, but basically it says if you don't have too wiggly of a function, then MLEs are going to be consistent. So the method of moments estimator is also consistent. But the MLE is already looking more attractive to us because it contains the sufficient statistic in there. So whatever these things are, whatever the bigger one is, that's my sufficient statistic. So I'm going to just leave it right there. We'll come back, say a little bit about Bayes when we kick off next time. I'll tell you what we need to know to define what the Bayes estimator is. And then we're going to jump tracks a little bit and we're going to do the expectation maximization algorithm. So next time, EM, a little discussion about Bayes, and then we'll clear everything up after we get through EM. And we'll talk about all these different criteria of estimators. But basically, showing consistency, how do you find estimators that are unbiased and they simultaneously have small variance, and then we'll talk about that trade-off between biasing your estimate and bringing down the variability. So that's it for right now. Have a great weekend, you guys. And I'll see you on Monday. Oh, sorry about that. Well, Ahmed is going to come in on Monday, and he's going to teach you the likelihood principle. So on Wednesday, I'll return and we'll do EM. So, okay, great.